Thanks for inviting me, Jens. It's always a pleasure to come to Meeting C++, both the conference and the user group meetups. Hi, everyone. Thanks for joining us so late, maybe for some of you. Some of you might know me. I've been involved with various projects for the past 20 years. I've always built tools. I've worked on Advanced Installer for 17 years, building tools for developers and IT pros. I built some open source tools that some of you might know and use. And recently, I joined the Visual C++ team at Microsoft, helping to improve the Visual Studio and VS Code experiences, the tools that I use every day. So if you have any questions, feel free to ask them, post them in the Q&A tab. I'll try to address them as they come along, if they fit a natural stopping point during the presentation. If not, I'll defer them to the end and make sure I address each and every one. And of course, I invite you to join the lounge after the talk, where you'll find me, and we can have an unplugged discussion around these topics and maybe share your experiences about the things I'm gonna talk tonight. And there we'll have a chance to be in a more relaxed context and chat freely about related topics. So what's so spooky about this this presentation? Some people ask me about the title, and it's really it's not it's not my quote. It's related to a famous quote by Einstein about quantum entanglement and the fact that the fates of tiny particles seem to be linked to each other, even if they're separated over long distances. And I feel this is strongly related to what I'm trying to show here tonight about objects, remote objects, interacting through loose coupling. And an alternative title for this presentation would have been Revisiting Observers, or maybe Subscribe to Observer. But I went for the catchy title. Right from the start, I'll have to say that I kind of hate the term design patterns. And the reason for that is that it implies that there are universally applicable solutions to some common code scenarios. And in general, just codifying existing practice into some rules, like a recipe that we can follow blindingly, it might be a comfortable path sometimes, but it's rarely the optimal one. In general, each situation is unique, and it usually has a unique associated solution best fitted for the business logic at hand. And in general, following recipes is not that easy anyway. But there is value in having a uniform code structure throughout the project, and these patterns, as we like to call them, because we tend to identify them and see them repeated throughout our code bases, have a value in easing understanding and easing extensibility of the projects, especially in a collaboration environment. So this topic is not to be discarded just yet, but it needs a discussion. I'm sure almost everyone is familiar with classic design patterns by the Gang of Four, as they're colloquially called. But I find it a bit too formal and dry. And for someone who is trying to familiarize themselves with these concepts, and these patterns, I would recommend starting with something more accessible and maybe more entertaining. And I would recommend Bob Nystrom's book, Game Programming Patterns, where we get to see common patterns in a more applied and presented in a more direct manner, with nice illustrations and examples. So for someone who's starting out to learn about these kind of things, I would definitely recommend starting with this book, and maybe then go for the classic Gang of Four. If you prefer the video format, I highly recommend this presentation by Klaus Igelberger from CPPCon, Design Patterns, Facts and Misconceptions. Short abstract here, just to give you a tease and maybe pique your interest. He talks about facts and misconceptions and common misunderstandings among developers about design patterns in general and about particular patterns in particular. And it explains, this presentation explains what good strategies of software design are, and how design patterns fit into these strategies and what these idioms imply in general, and with specific patterns analyzed. So feel free to watch this presentation when you have the time. Focusing on observer pattern, and this would be our main subject for this presentation. In terms of inspectable properties of objects, we have to think these years of object-oriented influence from other programming languages and from popular frameworks. What have we really learned from all of this thriving ecosystem of idioms and frameworks? And can we leverage these borrowed techniques in C++ in a value-oriented context, which is prevalent in C++ world? And does C++ benefit from other special considerations or issues that might arise from naive applications of the observer pattern? And we'll see examples. So we'll revisit our old friend, the observer pattern, from theory to practice. I'm not gonna try to offer the solution, but because I don't think there is one. But we're gonna examine trade-offs of several possible implementations and of several parts, tricky parts of dealing with this pattern in various scenarios from and with examples from a real project. Let's start from the basics 101 with observers. Observers are basically everywhere in various forms. If you can think about model view controller or model view model as frameworks of modeling UI, you can think about Qt signal slot mechanism that people might be familiar if you're using this framework. But it's not just about GUI and model interactions. This pattern also applies to model interactions and the way we send information across a network of objects and the way we couple remote objects. And I'm going to focus on that. So I'm not going to focus on typical idiomatic usages in popular frameworks like GUI frameworks. I'm going to focus on model-to-model interactions and these connections, these remote connections between objects. And I'll give them special names just so that we have a common vocabulary and I'm not too vague when I'm expressing myself. I'm going to call them actors and actions. My slides are also color-coded on this pattern for people that are able to observe these nuances. So a subject or an actor doesn't know the type the observers are. It just knows that they exist, and it has a means to notify them when certain actions occur. And this is how we express low coupling between these objects. So we have the actors and we have the observers, and the actors perform some actions that the observers might be interested in. It's a subscription model, and you can think of it as tuning into a particular radio station or a particular frequency. That would be the event that we're interested in from a particular object. And this is where inspectable properties of remote objects comes into play. And that's why I saw this connection with the spooky action at a distance. And we're going to see some spooky action for sure in a few slides ahead. So a very basic example here is we have a setter for a particular data payload. And when this is changed, we are interested in notifying some observer objects about the fact that the internal state changed, because they might need to do something as a result of this, as a consequence of this. So it's all about side effects here. The whole idea of inspectable remote objects is about side effects. And if we think about the subscription, because we're going to focus on the subscription and unregistration or deregistration. If we think about subscription, observers are added in a certain order, but we have to ask ourselves in terms of the intended use or the need in a particular application, do they need to respond in the same order? And furthermore, let's say we have them stored in a vector. Furthermore, how do we handle these registrations? Is a plain old pushback on our vector of observers good enough for subscribing? Is this the only possible strategy? What about adding an observer more than once? Let's say we don't want to allow this to happen. Then we might do this check before adding a new observer to see if we already have it registered. But there are situations, practical, valid situations, where you might want to register the same observer twice. And we're going to see some rationale about this when we talk about local reasoning or subparts of a particular function or task within an application. So in the situation where we do want to allow oversubscribing, do we expect the observer to be called twice for the same event? And how do we differentiate between the two instances? We're talking about the same object instance, but I mean the two sequences of registration, which was the first one and which was the second one. Do we notify both of them? And if so, in which order? And this is relevant for local reasoning. It's easy to analyze this idea in if you have a global view of the object network, and if the application or the interactions are fairly trivial, like in toy examples, it's fairly easy to reason about these kinds of things. But in complex object networks and in large applications where components might be very far apart, or even more where you might have components that are pluggable, or components which can appear and disappear from the system. And these components, while registering in the system, let's say a plugin or something like that, might become interested in receiving event streams from the framework that they register into. And when they are on the other side, when they're unplugged, we need to stop sending those signals to those components. So the image here could get complicated. But in let's say we have a, a local scope or a local function that might be doing something important, and they need to receive a particular notification while doing this block, while executing this code block. And it will choose to register itself at the beginning and deregister at the end, and receive events for the duration of this code block or this particular action or tasking within the application. So the obvious problem here is what happens if the observer was already added before, and in our local reasoning, because we don't know what happened outside of our scope, we're trying to be careful and not depend on outside states. So we add and remove because we're interested in these event streams. But at the same time, we don't have, as this is constructed, we don't have any information to know if we are the only ones registering this instance or not. And I specifically chose the this as observer so that it's obvious that another function might have done the same. So fairly easy solution in this case would be to have some kind of RAII register object that can keep track while constructing, to keep track and hold on in internal state the fact that it was the one that the first one that registered this particular observer, and subsequently deregister it if that was the case in the destructor. So in order to do that, we have to signal, our register function has to signal out the fact that the registration was successful. So it was the first time this observer was seen in the system or not. So going back to oversubscribing and adding an observer more than once. And so we're removing the check for the existing instance. If we're oversubscribing, do we expect the observer to be called twice for the same event? And this is tricky, and in some situations there are legitimate cases where you would want that. But there are other complications regarding particular order of registration and notification, again related to local reasoning and restricted lifetimes. So if we're talking about unsubscribe and removing observer, in case we actually are, it is meant to be removed, and we're not in the situation of oversubscribing, then it's fairly easy. But in the multiple registration scenario, we might find a particular observer in our collection and choose to remove it, because that was we were instructed to remove it by this API. But how do we know if we are removing the wrong instance? If we're removing, if we have it registered in position 3 and in position 48, as the code is written right now, it will remove the first one that is found, and that might not be what the code expects. So in general, of course, it's not good practice to be sensitive to the order of notifications. So the code should be really resilient in case two events are fired, and multiple observers are notified about a particular event. In general, we should not be sensitive to the order of notification of different observers. Like observer A was notified before observer B. So in general, it shouldn't be. It shouldn't matter. In reality, these events and their implementation blocks are not pure functions, and are modifying some kind of state in our global network of objects. So they do have side effects. So in particular cases, code might be very sensitive to the order of notification. So now if we remove the wrong position, the wrong instance, although it's the same object, but we remove it from order of notification 3, and we leave it in the position 48, now 47, because we're sliding, so there are fewer observers in the list. We changed its relative notification order relative to other still extant observers for that particular event. So bugs will happen. So we have to be very careful in situations like this. And I'm not saying they are outright bad ways of organizing code, because there are legitimate situations where you do need oversubscription. But we have to be very careful with unsubscribing and about the sensitive order of notifications. If we choose to take the route of removing all instances, then it's easier, fewer complications, but it's not always possible to do this. And I never miss an opportunity to teach about a safer pattern in modern C++. Instead of using the awful erase remove idiom, prefer to use the C++20 function that is much safer and much cleaner than the erase remove idiom. I have a short presentation at ACCU about the perils of erase remove idiom and a good rationale to go for the C++ safer option. The video will be out in a few weeks, I'm sure. Is still in processing. So who should be notified first? A particular valid strategy might be to treat this vector as inserting at the beginning every new observer, so that we have some control of the notification order. This might be a valid case in some scenarios. I've seen this done. I've seen other strategies of generalizing this and building priority buckets, having various rings of observers, like most important observers, less important observers, or when we talk about sensitivity to the order of notifications. So we may have ring 0 observers that need to be notified before all the other ring 1 observers and before all the other ring 2 observers, and so on. So there are valid situations where you might need to construct specific priority buckets to group notifications relative to each other. So I've seen strategies like this. And then we can amend the API and have something like this and pass the priority as a parameter. But what happens if we have an observer is registered? If an observer is registered by mistake with a different priority? In the model of oversubscribing, we might have the same observer registered with let's say ring 0 the first time and registered with ring 1 the second time. And what happens then? And because weird side effects might occur if they're notified in different rings, and even more complicated scenarios around deregistering these observers. So we need to be very careful about using these patterns. And now on the other side of things, where after we have the observer network all set up and we have all the connections linked, let's talk about the mechanics of broadcasting these events. And very simple implementation might be traversing our container of observers. We had the vector previously. So traversing the vector of observers and for each one trigger a particular event. Let's say the widget changed from our previous example with the data setter. That would be the broadcast. On the other side, the observer, some observer, because there might be many, some observer will tune in and it will receive this notification from the actor and react in some way to the changed object and maybe query something about the sender of the notification and so on. Maybe ask for the new internal state or the new value, something like that. But there is an interesting particular case that I've seen pop up, and that is the one-shot observers. That's what I call them. And that is when an observer registers for a particular event and cares only about the first occurrence of that event. So after the event happens, this particular observer doesn't want to receive further notifications from that particular sender about that event. So one way of dealing with this, and I've seen this in practice, is that while we get the notification, let's say widget changed from this actor, we do something that it might be important to react to that change, and then we deregister ourselves. So remove observer of this being this instance of same observer, and we deregister because we don't want to receive further notification. We're done. We've seen it already, and we don't want further events like this. Where there's a problem here, and the problem is that there's a chain of invocation. If we're following the call stack, it's more obvious, and it's easy to see when we call this actual event handler widget changed. We are doing this in our for loop that traverses the registered observers for that object. So while we're inside this callback widget changed, in a synchronous manner, we call remove observer, and that causes our erase implementation from remove observer. We've seen it earlier when I mentioned the erase remove idiom. So that in turn calls erase and removes this instance from our observer list. But we're happening to be inside the iteration loop for this observer list for this vector. So we're removing something from this vector while we're iterating it. So trouble. There's a kind of a classic idiom or classic fix for these kinds of issues, not just observers, not just for observers, and that is to use zombie positions or using sentinel values instead of deleting those instances. So instead of erasing, we're placing a sentinel value. In this case, because we're holding pointers, we can place a null pointer there. And then we clean up. And the reason why this works is because we can, when we notify observers, we have to, while we traverse our list of register observers, this list now may contain zombie observers or observers that deregistered. So we have, and we now have that sentinel value of null pointers. So we have to add an extra check to see if that observer is still there before sending a notification. And of course, we have to do some cleanup at some point and remove those instances from our collection. And that is easy too. Another case, particularly when we're dealing with complex systems or nested functionality that might need observers, is that we have recursive adds, but they are more rare in practice. And the problems are similar as the problems we've seen with recursive remove observer. Another issue around such object networks is that sometimes we're dealing with really small objects, and these small objects might be interested in having observers and notifying about particular changes. Let's say a simple case like inspectable property, like a data setter. But if we're dealing with small objects, then um, it's not always affordable to have an intrusive list of observers in that small object, because first of all, um, we do pay the cost of actually having a vector there, and maybe many instances in our network of such small objects, because in many scenarios when we're dealing with small objects, we tend to have lots of them, and um, some or many instances will never have a registered observer. So they might have this ability to have observers, but they might not register any. So then we would pay the cost of storing an empty vector in each of these object instances, and an empty vector is not tiny. So in many situations, this is not acceptable. One way to deal with this that I've seen in practice is using some sort of lazy structure, like a lazy vector, let's say, where we make use of operator star and operator arrow, and we fold in the vector lazily the first time it's needed. So in general, we just pay the cost of a pointer, and in the situation where we actually need that instance actually needs observers, then it will create on demand a new vector where it will hold the collection of observers. And when the last one deregisters, we can also deallocate this block. So fairly common strategy that I've seen to deal with this. But if we have lots and lots of these, again, might not be the best practical solution. And even in that situation, storing a pointer in those objects, again, might not be practical. Even the cost of a single pointer in that structure might be too much for some scenarios. So another strategy that is in use is to have an aside lookup structure, a lookup record of all observers for each object. So I intuitively named it global bottleneck because kind of is. And we can have a mapping of all these records for each actor that has gained some observers. We have its collection of observers associated. So in this aside structure, it is a bottleneck because if we have lots of these instances flying around, okay, you no longer pay the cost of storing it intrusively, but now we are going to hit this global data structure, and you're going to have contention on this structure for all your objects in the object network. So might not be the best strategy for all purposes, but it is a strategy that people might want to use. If we're talking about threads, because we have to acknowledge the presence of threads and we have to deal with them in our object networks. I like to call threads like multi-lane highways to crashes, because sometimes they are. And the immediate solution to this is to use a mutex, and we have to guard each such function. Let's say from our previous examples, that setter, the add observer, remove observer, and the notify functions, they all have to be guarded by such mutexes. And if we're going back to the recursive add or recursive remove scenarios of oversubscribing, first thing that comes to mind is using recursive mutex, of course, because the name is right there. But as it turns out, using recursive mutex is almost always a bad idea. And you can easily get yourself into deadlocks. So it's not bulletproof. It might work in a particular fairly simple scenario, but you might end up deadlocking easily in the future. So more about that later. I talked about values at the beginning in our C++ universe, and squaring the circle, as it were, a value-oriented design in an object-oriented system. When we're talking about objects on the heap and object networks and reference types, how do we reconcile that with value-oriented design, or ephemeral objects that are created, moved, and destroyed fairly quickly? I do strongly recommend this presentation by Juan P. Bolivar Puente, Value-Oriented Design in an Object-Oriented System. It's a very good presentation. You can find it in multiple incarnations, some older, some newer. I've linked one of them here. It's a fantastic presentation that goes deep into scenarios and a case study of a library to deal with such situations, and how do you compose operations and deal with values and kind of use the type system to achieve things that sound very functional in way, but it's at the same time very C++. So I do encourage you to watch this presentation if you haven't seen it already, or maybe watch it a second time. I know I did. So when in doubt, always make copies. That would be my recommendation around threads. It's always safer to make copies and move things around than actually trying to protect stuff. And with that in mind, if we're going back to our notify observers function, where we traversed the list of observers and called our broadcast event, which is changed as we called it. And a potential fix for this would be to actually have a copy of the observer list and use a plain old mutex to just very regionally protect where we need to. For example, when we copy the observer list, when we modify the observers, and when we traverse to broadcast this event, we're actually going to traverse the copy we just made. So we don't hold the lock for the whole duration of the event broadcast. So I think this is important. I failed to highlight this on the slide, and maybe I should have. It's important that we don't hold the lock for the whole duration of the broadcast, and I'm going to mention that why that is immediately in the next slide. It's in general, it's important to hold a lock for the minimum amount of time needed, and even more important to be aware of holding locks when calling external code. And when we're broadcasting this event, which is changed, we're calling into external code, so we don't know what those objects will do as a reaction to this event. And for sure, building a copy and traversing the copy avoids the issue with iterator invalidation and with corrupting our observer container there if someone decides to re-register or unregister as a consequence of this broadcast. But the code is messy, and there are situations where even this combination might fail. I promise I'm gonna go back to and explaining the holding the lock portion of that slide. But before I do that, I should probably need to point out that there is functionality that is worth studying, and that is from Qt framework. I would encourage you to look into how delete later from QObject works. In general, even if you're not using Qt as a UI framework, I think it's instructive to understand how this mechanism works. And yeah, it's very related to the things I presented here. So that would be homework material. Yeah, if you're interested to learn more about idioms like this. Um, of course, I have to pitch the presentation by Tony from a few years ago at C++ now, around thread safe observer pattern. And there, in this presentation, which is it's basically just a full-on demo rather than a presentation. Tony goes through several scenarios of registering and unregistering observers and firing events at various uncomfortable moments and breaking the system in all the ways possible. And there you're going to see events in the wrong order and crashes, and even when we're almost sure that now he's got it right, he nailed it down, it's gonna work. He will find a way to disappoint and find a corner case where that it will fail. So a very instructive and at the same time disappointing outcome, in that it's very difficult to build a robust object framework with in the presence of the observer pattern. And the idea there is not to dismantle this pattern or to discourage its usage. The idea there is raising awareness, the very same thing I'm trying to achieve here. In that there are very useful cases and there are tremendous advantages of using this low coupling mechanism in complex object systems. But we need to be aware about the particular situations in our in our application, and how best to implement a particular strategy that we need. So definitely worth watching this presentation. It's highly entertaining. So going back to threads, I promised I'm gonna explain the holding the lock portion of that previous slide. In a multi-threaded context, it's almost impossible to implement a solid observer pattern, and that would be the takeaway from Tony's talk I mentioned earlier. And in real code, you can't see the deadlocks until they happen. In toy examples and anything that we might build up here, and in Tony's examples, which are fairly trivial and easy to see at a glance on a screen, it's obvious when a deadlock might happen. If you have some experience with deadlocks. But in real code, when we have complex interactions and far away reaching codes, you won't see it until it happens, until you hit a particular corner case and it happens. And the rule of thumb there would be, don't hold a lock while calling unknown code. And that's why I was explaining that holding the lock while broadcasting the message, it's a very bad idea, because broadcasting the message means you're calling external code, and that code might end up indirectly taking that lock that you're holding. So you'll deadlock potentially and not even know it. But in general, holding a lock while calling unknown code has consequences, and better not do it. Some say that it's code smell, that you need to do that, but in general, it's not a good strategy. So anyway, Going back to the intrusive nature, because so far all we've seen is intrusive designs. We would want to encapsulate all this functionality into a separate, let's say, actor facility that we might reuse. In this situation, I named it actor, and it's templated on the particular widget that might use it, and it will inherit all the necessary boilerplate, because you don't want that in your mixed with your object functionality. So on the other side, for the remote observer, most probably we would define a narrow interface there, a narrow protocol, let's say iObserver, and we register on construction, let's say, and deregister on destruction, and we override a particular event. Let's say we might have a list of potential events that we might care about, and do something as a consequence. And of course, we don't have to forget to cancel. So always strive for something that is fairly automatic and easy to keep track of. So something like RAI. I have to mention optional protocol methods because this is something that we don't have in C++. Other programming languages, let's say Objective-C or Swift, have optional protocol methods. So we have to deal when we define this interface between our actors and observers. We might have plenty of events that might possibly be fired up. So a particular observer might not be interested in all of them. So classic way of dealing with this is having stub implementations, and our spectator observer will actually implement the observer interface indirectly via this stub class, so that this particular spectator will override just the going to sleep event, because they don't care about all the other events that might happen from a particular actor. So fairly easy but necessary boilerplate, because we don't have actual language support. So yeah, if we have, let's say, now we have the situation where in a particular spectator, in a particular observer object, we're interested about multiple actors and multiple actors triggering, let's say, the same event. We're interested about going to sleep event from multiple actors, and I'm going to try to name them differently so that there's no confusion. I'm going to call the first one, the first type, let's say it's an actor, and the second type is a thespian, and our spectator is interested about this very same event or events, but just one would be enough to complicate things. So we're interested about the going sleep event from both actors and thespians, and we see the registration fairly intuitive. We add ourselves, so we are the spectators. This is spectator, so we add ourselves as observer to the actor and as observer to the thespian, and remove the same. But we have a problem here, because we have the same callback function, we have the same event name, and how can we reconcile that? And as always, every problem can be solved with another level of indirection. And the solution here, and if, by the way, if you recognize this pattern, you've been probably writing C++ for a while. It comes out of the Loki library by Andrei Alexandrescu. And we can use the technique of using a type tag here, and we construct a type with this facility into type, let's say. Fairly trivial way of constructing such a unique type. And the way we're going to differentiate is using observer indexes, let's say 0, 1, and name them so that we have unique instances. And how will that work? So our staff observer will have various, it's now a template based on this observer index, and it will have various event names here. But the first parameter of each of them is this type tag that we're going to use. And we have to build a proxy. This is the level of indirection I mentioned earlier. We have to build an observer proxy. And this observer proxy will be the one that implements the observer interface that we define, our protocol. And it will take a concrete observer and an observer index. So it will be the unique type ID. And because this proxy that we're building is the one that implements the protocol, the observer protocol that we have in place, it will have the two, let's say the two events, stuff added and stuff removed. I've named them here. So these will be unique functions in this observer because this is the one we're adjusting. So they come from, you see the override keyword, they come from this protocol. I color coded them appropriately. And inside, they will call the appropriate stuff added and stuff removed, the corresponding event names, from the actual observer, the ones that have this type tag, the ones that we defined on the previous slide here. So they will call the appropriate method by constructing a type ID object just for the purpose of tag dispatch here. So no other purpose but to pick the right overload. And we define them easily. Let's say for the example that we set out to build, our actor would be a staff observer, the first one, index 0, and its proxy would be staff observer proxy of spectator with index 0, and the other actor type, we call it thespian, will be a staff observer 1, and its proxy would be staff observer proxy of spectator n1, where spectator is the observer that is interested in both actors and thespian events. And now, when we define our observer, our spectator, that is interested in both actors and thespians, so it will use them as bases. So there will be staff observer 0 and staff observer 1. These are the type aliases. And when the spectator is created, it will add as an observer the actor proxy to the actor rather than add itself like we had previously. And it will add the thespian proxy as observer for the thespian type, not itself. Previously, we had add observer of this. And this will construct this indirection. So every time a notification will come, it will come to the proxy, and the proxy will forward it to the appropriate spectator, which is this one, but to the appropriate overload of the event in the spectator. So if we define the spectator implementation, we can see we have two events that are called going to sleep. So there are two events, but they are distinct functions. One will take a type tag of the type observer proxies actor type ID, and the other one observer proxies thespian type ID, which is just a tag that will help us build an overload set. And now our observer has a regular structure where we can clearly see that this event was triggered. This event is called going to sleep, and it was triggered for what type? It was triggered from an actor type. And the other going to sleep event, it was triggered from the other type, our thespian actor type. So we can differentiate between them. So we can have multiple events from multiple actors all within the same spectator. by using this technique of using proxies and registering the proxies as direct observers, and the proxies in turn will fire up the right overload in our spectator class. So I found this technique very helpful. And furthermore, the staff observer and staff observer proxies that I showed in the previous slides can be used for any other spectator type and for any subjects and actors. The only specific part is the protocol part, or the interface that is used. So the everything else is usable. So we can use these template classes. We can use them for different actor types, so different senders, and in different observers. So we don't have to build new ones. The only specific part is, again, the protocol. So the events that are mentioned in that interface. If we have different set of events or different protocol, then we will need to build a different such reusable components. This is a very useful pattern to leverage multiple tuning into multiple events from multiple senders at the same time. In closing, I'm gonna mention a little bit about global state. In general, this pattern comes into play when we have observer networks, and in general, observer networks tend to form global state. And we have to be very careful about all these interactions. And this is kind of the same reason why I dislike shared pointer. Everyone who knows me knows I really dislike shared pointer, is that it helps you build huge object networks and it builds global state and global connections between those objects that are sometimes very difficult to reason about. And one particular consequence for using the observer pattern in such networks is that you can easily end up in memory management issues. You can end up with dead subjects while having these observers active and running. You can then end up with missing observers, and you can be blissfully dangling. So we have to be very careful in how we orchestrate this dance of registering and unregistering, and do it in a civilized manner and doing in a consistent way. Let's say associated with construction and this deconstruction of objects, or in particular actions that are symmetric in their behavior or in their lifetime implications. So if we arrange that we do our registrations and deregistrations carefully, then we can avoid hitting memory management issues, because they tend to be associated with improper usage of these loose coupling methods. So we have to be careful not to end up like our funny little sketch with a dead parrot. And with that, thank you for tuning in and being good observers. And I'm open for questions if you have them now, or I'll meet you in the lounge for unplugged Q&A.